Hello. Yeah. Hi, everybody. Thanks for hosting me today. I'm very happy to talk here. My talk is about bridging the gap between secure hardware and the Kharkov's principles. About me, yes, as Florent said, I'm a former student of EDCEMAG. That's why I'm very happy to talk today here. I've been working for 10 years in the secure hardware area, and I joined Ledger, which is a company which designs security solution for blockchain application. And in blockchain application, the transparency is a top priority. On the contrary, in the secure hardware, transparency is not a priority at all, and I'm going to try to explain how we are trying to bridge this gap. Well, the agenda, so first I'm going to introduce the secure hardware world. Second, a word about open source, how open source meets the Kharkov's principles. Then I'm going to talk about how we're trying to bridge this gap. And finally, I'm going to give a word about our last year CTF. Well, during the past decades, the security industry, when they wanted to build a secure system, they chose hardware-based security solution. The idea behind this is to put all the security of the system in a single point, and often they use smart cards. Because smart cards are a very good way to store your secret data and to implement your security in a hardware enclave. This is secure hardware. This provides a high level of security, but it's a very opaque world, so we can wonder if it's security by obscurity or if it's really secure. It's really secure, but it's a lot of obscurity. Today, we can take advantage of 35 years of smart card legacy. This is a very well organized security industry with big actors, IC vendors like ST, NXP, and others, and embedded software developers like Gemalto, Guillemet, and others. They organized an evaluation and certification process, which is well defined. The most popular certification process is common criteria. It defines different level of security, and the highest level of security for smart cards is EAL5+. This process consists in a third-party evaluation, and in this framework, the threat model is the attacker is supposed to have physical access to the device. So a lot of different attacks are assumed, like software attacks, side channel attacks, perturbation attacks, and even physical attacks. I've put a star on physical attacks because actually during the evaluation, the physical attacks are overrated, so that even if physical attacks work, at the end, smart cards can be certified. And for me, this is a bit confusing because on the field there are hacks, there are hackers who are able to break smart cards using physical attacks. So it's a bit a pity to not really taking them into account. I think the main problem is that if an evaluation body is able to break a smart card using physical attacks, the IC vendors are no choice but manufacturing another IC, and it costs a lot of money. And this is the main reason why it's not considered. This is my opinion anyway. What is hidden on smart cards? The hardware design is completely proprietary. Even the datasheet is proprietary. It's not possible to get the datasheet of a smart card. The embedded software is also hidden, proprietary. The countermeasures are proprietary, hidden, so on. And even the attack methodology and the evaluation process is not public. So we can wonder why this obscurity. There are several reasons, according to me. The first one is intellectual property. The vendors try to get the secret for them and keep the advantage according to their competitors. But in practice, engineers go from an IC vendor to another one, and the IC vendors study their competitors, they reverse them, so each vendor knows pretty well how their competitors' smart cards work. So this is not the main reason. For me, the main reason for hiding this data is common criteria itself, because on the common criteria methodology, you have an advantage to keep this data secret. In the rating methodology of common criteria, the knowledge of the two is a criterion, and it gives more points, and it gives an advantage to get certified more easily. In an evaluation lab, there are some strange discussion when the evaluator is able to break a smart card using an attack. He calls the vendors, and then the vendors often tries to negotiate the rating of the attack in order to put the attack out of the scope and to get certified without patching it. It's a bit disturbing, right? We can wonder also, does the obscurity actually work? We have several examples where the obscurity miserably failed, like Canal Plus. Everyone knows this example. MyFair was also a proprietary algorithm which was reversed by security researchers. And more recently, there is this Roca story when Infineon designed the fastest prime generation on the field. But that was for a reason that they use a fast prime generation in a very small space with a given equation, and a security research team in Czechoslovakia or Czech Republic retrieved this equation, implemented Coppersmith attacks in order to factor RSA key generated with this generator. It has a huge impact because a lot of ID cards in Estonian, for instance, have been collected and updated and so on. So at the end, it does not really work. But there are also examples where this obscurity works, but we can't talk about them, of course. Well, what I said about secure element is not very good, but nevertheless, it remains the best option to secure data today. So from this, going to the blockchain, in this world of transparency, there is a huge gap. In the blockchain world, everything is open source. The open source grants the user the possibility to study the code, to find vulnerabilities, to patch it, and so on. This process is ongoing. In the cryptography as a science, this is exactly the same thing. Researchers always try to challenge the algorithm in the standardization process, and even in the cryptography in general. So this world completely meets the Kirchhoff's principles. And at Ledger, we try to build a secure system for blockchain application. So secure system means secure element. But how can we bridge the secure element world to the open source of the blockchain and the science? So we built the first native open platform based on a secure element. It's based on the ST31, so a certified chip. There is an attestation mechanism which allows you to be sure that your device is a genuine one. And we implemented an OS which is called Bolos. Nice name. It means Blockchain Open Ledger OS, and it's a native OS. The model looks like a bit Java card model, but it's a native one. For the isolation between the apps and the kernel, we leverage the property of the smart cards. We use the MPU and so on. It's not the case in the Java card world. And we allow our user to implement their own app, their native app, and they can load it on our platform. We provide a large cryptography API, which allows you to implement your cryptography, and the cryptography is implemented directly on the secure element, providing you a high level of security. Our API today is quite large. We have a lot of different cryptography algorithm, and it allows you to implement cryptography in the highest level of security possible in a native way on a secure element. The problem is that Bolos cannot be open sourced because we have NDA with our vendor, and those NDA prevents us to open source our OS. This is unfortunate, but we are going to try to make an open source version of our OS, removing all the proprietary part in our design. But our apps are open source. We mostly sell this platform for cryptocurrency applications. So we have all the apps for Bitcoin, Ethereum, and so on, which are open source, and you can load them on the device. But we also have security application like password manager. You can also implement your SSH key inside the secure element and mount your SSH tunnel between the secure element and your favorite servers. The same for PGP and so on. And you can implement your own app. We have a signature mechanism so that we are able to sign our application. But if your application is very good and so on, you can submit to us. We will review it, and if it's okay, it's secure and so on, we will sign it and put it in kind of store. Security is not just a claim. We are trying to attack our system all the time, and we've built Donjon. Donjon is an open source lab, security lab. We implement side channel attacks and perturbation attacks and also software attacks, and we're trying to open source our attack tools. We recently open sourced Lascar. Lascar is an open source side channel attack library. It's used to drive your test bench, to synchronize your trace, to implement CPA, DPA, machine learning based attacks, template attacks, and so on. It's very convenient and written in Python. And we are also working on Lemur. Lemur is an emulator based on Unicorn, Leaf, and Capstone. It allows you to trace your binary and to inject faults on it, and it's very convenient. I'm going to show just a quick example. On the bottom, it's not very clear, but on the bottom you have a side channel trace, which are measured directly on the device. We took a lot of trace and then implemented NICV and SNR in order to retrieve data-dependent side channel leakage. And in order to understand where this leakage is from, we implemented the same using Lemur. On the top left, you have the assembly of the program, and then on the top right, you have the side channel of this program emulated, and it allows you to understand which instruction actually leaks. it's very convenient to implement secure side channel code. We also are about to open source fault attacks tools. We have a nice laser attack test bench, and we will open source the tools to drive the test bench, and also put open hardware our board, which is called Scaffold, and it's used to drive the test and so on. We also have the bounty program, which is very common in the software world, but in the hardware world it's pretty unusual, meaning that we encourage security researchers to try to break our system, and if some vulnerabilities are retrieved, we give some bounty to this researcher using Bitcoin, of course. And we have a yearly CTF and the hardware bounty. I'm going to talk about quickly of the last year one. Last year that was 2 steps CTF. The first step was pencil paper CTF. There was a mathematical problem around RSA, a non-reuse problem around Bitcoin, and also a kind of white box AES. And the contestant which get qualified got a dedicated hardware bounty, on which I'm going to talk about after. But first, I'm going to give a word on this kind of white box AES. There was a lot of interest about this problem, so that's why I wanted to give some word. That was non-stripped Linux 64 binary, which implemented an AES. The user has an input, 16 bytes input, and the program was computing an AES and with a key hidden in the binary, and at the end compares the result with a constant. And the problem was to find the input, which was encrypted to this constant. But of course, there was some countermeasure. The countermeasure looks like the kind of countermeasure you can find in the hardware world. First of all, there was a fake AES, only one real AES among 14 fake ones. There were also random scheduling, which was scheduling different AES randomly. Also, there were linear first order masking in order to mask the data during the whole computation, including subbyte, mixed column, and adjoint key. The linear part are easy, but the SBox part was a bit trickier. And also, there were an infective fault attack detection, which was computing a kind of CRC of the binary. And if an attacker tried to modify the binary, this CRC became wrong, and the whole AES became completely faulty. What was quite fun was the different answers we received. After a few hours, there were the professional reversers which said, I don't understand what's difficult, everything is easy. I put it on IDA, remove the countermeasure, and within a few hours, I retrieved the key. So this is a kind of answers we received. We also received some answers where people spend more time, maybe 10 days later or more. Some people said, oh, I tried to implement GFA, I couldn't set up the tools. I tried side channel, it never worked, everything is masked. And I finally reversed it using objdump and GDB. I lifted it in Python, and I finally was able to inverse the first box. A lot of work to break this challenge. I also have a nice solution using GFA. This one was quite interesting. The idea was to remove, using GDB, remove the anti-GFA countermeasure, and then inject a random fault in the 9th round of the AES, And finally, using side-channel marvels, implement a classical DFA based on pirouette and quizquater or something like this. And finally, a side-channel one, which was quite interesting as well. This one used a unicorn to emulate the binary execution. And using unicorn, he hooked the random function in order to put constant instead of random. And then it allows him to prevent countermeasure and to remove the masking of the S box, and so that the whole execution becomes unmasked, and then he implemented a side channel directly on the binary trace, just as I explained with Lemire just before. Then the contestants which were qualified got this hardware bounty. This is a dedicated hardware which implements scalar multiplication from a private ECDSA key. It computes the public key using the scalar multiplication. And what was fun is that this private key allows you to get access to more than one Bitcoin. So the contestants were very motivated to break it. But there were a lot of countermeasures implemented on the hardware. On top of it, that was a secure element, so that was definitely difficult. There was also a kill card mechanism for the fault attacks. Physical attacks remains possible. As I said, it's always possible to implement physical attacks, but it costs a lot. I don't think you can. It's positive if you implement physical attacks. It will cost more than 1 Bitcoin at the end. So that was a side channel challenge at the end. So the idea was to retrieve the key using side channel. And that was definitely not an easy challenge because there were also side channel countermeasure. The vertical attacks were not applicable because of the countermeasure. Only a specific kind of horizontal attacks were possible. And the only one team won the challenge. Of course, that was the same key on each device. And they spent 2.5 months to be able to retrieve the key and get the Bitcoin. Additionally, we offer them 1 additional Bitcoin because of the amount of work. This is Ninja Lab, so I want to congratulate them because they didn't know the implementation. There was also some jitter on the trace. And they were able to extract the key and sign the Bitcoin transaction to retrieve the money. At the beginning, I was intending to present this attack and how this challenge was exactly prepared. But again, bridging the gap between the secure hardware and open source is very difficult, and I've been prevented to present this. So sorry for this. This is the end of my presentation. If you have questions, I'd be happy to answer them.
So thank you, Charles. Do we have any question, Camille?
Hi, thank you for the presentation. From what I understand, in Lemire, you've been able to emulate the side channel for each instruction. How do you do that?
Yes, good question. Thank you. Here, on the top left, you have all the instruction, and you only have to write the value of the instruction, then the operands just after, and you form a trace with this data. You have instruction, operand, instruction, operand. Then you have a long trace. Then you change the value of the data in your binary emulation. You get another trace, and so on. This is exactly as you could get from the power, but this is emulated. And then you only have to implement NICV or SNR. And if you have a data dependency, you will get these peaks on the top left, top right. And what is cool is that you can scroll with your mouse, and you will know which instruction correspond to which peaks. It's very convenient to implement a countermeasure on your code.
Thank you.
Welcome.
Any other question? I got at least one question. What are there any publicly available information or write-ups on the different challenge that?
On the challenge, on the 3 challenge, yes, they are available online.
Oh, I've just missed the point. Okay. Okay.
Online, but for the last one, I hope that Ninja Lab will be able to make a write-up explaining how they break. But for now, we can't.
Okay. Thank you. Merci, Charles.